Hi, I'm Alex Moody. I graduated from UNH in 2019. I now work for Woodard & Kern as an engineer in the drinking water practice. I'm here with Rob Little, who's going to take us on a brief tour of the university's brand new state-of-the-art drinking water facility.
Thanks, Alex. So this project replaces the original plant, which was built in 1935. It's the result of several years of careful planning, design, and construction in partnership with the university and the contractor.
I've heard a lot about this project, and I'm excited for this tour. Why don't we head into the facility?
We will, but first I'd rather go to where it all begins, the Lamprey River. The intake station over there is not part of this project, but it's a critical component in delivering safe, potable drinking water to the university and the town of Durham. We're about 2 miles from the treatment plant at the intake station on Lamprey River. This is one of 3 raw water supplies for the plant. Wiswall Dam, about a half-mile downstream, maintains the water level here. An intake screen in the river behind me allows water to flow into the basin of this small building. Low-lift pumps deliver that to the plant. The Supervisory Control and Data Acquisition, or SCADA system, controls these pumps remotely from the treatment facility.
Some water is pumped from here directly to the plant for treatment and distribution. Water can also be delivered to aquifer recharge basins near the Spruce Hole well. This helps UNH adhere to its complex water withdrawal permit, balancing the demand for potable water and fire protection with the need to protect the environment and the natural water resources. Here we are at the Spruce Hole well, about 1.5 miles from the treatment plant. When there's sufficient flow in the Lamprey River, the recharge basins here can be filled with water. That water flows down into the aquifer. Later, it can be used when the river flow drops below a certain threshold. The pump station here withdraws water from the ground and delivers it to the treatment plant.
Oyster River is the third and final source of supply for the plant.
Water level here is maintained by the Oyster River Reservoir Dam.
Water enters the structure behind me and flows by gravity to the Oyster River pump station, where low-lift pumps deliver it a short distance uphill to the plant. Now that we've seen the sources, let's go look at the treatment process.
Water enters the treatment plant here from any one supply or blended combination depending on demand and source water conditions. Operating reliably with any combination of the 3 supplies, each with different water quality and hydraulic conditions, presented a unique challenge in the design of this facility. The raw water flow is all managed by operations staff who use a customized SCADA system, this control valve, and a series of online analyzers to always ensure that flow, pressure, and raw water quality are optimized. After raw water pumping, the next step in the process is chemical pretreatment. Chemicals are added through these injection quills. First, polyaluminum chloride is added for coagulation, which causes dissolved solids and tiny particles to combine into larger particles called flux that are easier to remove in later treatment steps. Then, sodium hydroxide is added to adjust the pH. Plant operators monitor the pH to ensure it is balanced accurately for optimal effectiveness of the coagulation chemicals. Sometimes, potassium permanganate is added as an oxidant to help remove manganese, which naturally occurs in the source water. Inline mixers, upstream and downstream of the chemical injection quills, ensure that the blended flow stream is uniform and that chemicals are thoroughly mixed. Notice that there are several pipes and sets of mixers. In the design process, we must always consider if something breaks, what happens. Building redundancy into the design greatly reduces the likelihood of needing a complete shutdown, which can be disastrous in water and wastewater treatment facilities. As we continue the tour, you notice that all critical equipment and process basins have redundancy, at least 2 to 3 independent systems, which allows 1 or 2 to be shut down for routine maintenance, emergency repair, or replacement without impacting the plant's ability to produce high-quality drinking water. Flow meters monitor the flow into each of the 3 process trains. We're now standing about 15 feet above the floor, looking down into the flocculation basins below this grading. These mixers move the water slowly, causing the small particles to collide and merge into larger particles. Those particles will settle out faster downstream in the clarifiers. The motors and paddles in the second stage of flocculation in each train spin slower than the first basin. This ensures that the particles continue to collide, but with less energy so the larger, more fragile particles don't shear apart. Downstream from the flocculation basins, the clarification process begins. In this plant, we have sedimentation basins equipped with inclined plates that shorten the necessary settling distance. This allows for better treatment in a much smaller area than required by conventional basins. Water flows into this basin, around the bottom of the plates, out the top, and over the weir into the collection troughs. We want to see this nicely formed flux slowly entering the clarifier basin, ready to settle out. Because the solids need to sink, we need to limit the upward flow and the velocity of the water. Once the solids settle and accumulate on the plates, they slide down to the bottom where they can be removed. In this case, the solids, often referred to as treatment residuals or sludge, flow to a lagoon system outside that you'll see later. Clarified water from each of the 3 treatment trains flows into a common channel below this grate. This channel is designed to provide operators with the flexibility to go from any clarifier to any combination of filters. This decoupling allows operators to take processes out of service for maintenance or repair if problems arise. This plant has 4 filter basins or beds. Operators control which of the 4 filters are in service by manipulating the weir gates in this channel. This can be done automatically through the plant's SCADA system. The filter media consists of 36 inches of anthracite and 10 inches of sand. That's supported by an underdrain system. The tiny spaces between the grains of filter media trap remaining particles while allowing water to pass through. These filters were designed with extra unused depth in case granular activated carbon, or GAC, is needed in the future. Eventually, enough material builds up so that water can no longer pass through efficiently. At that point, the filter needs to be cleaned using a process called backwashing. Depending on raw water quality and flow, each filter in this plant can treat water for approximately 4 days before requiring a backwash. At the end of each filter run, forward flow stops and the backwash process begins. First, water is drained down part way. Next, air is bubbled up through the media in a process called air scour. This begins the cleaning process by mixing the filter media particles and causing them to bump into one another, loosening any trapped material. Treated water is pumped upwards through the media, expanding and mixing it and flushing out unwanted particles. Backwash waste is directed to the same lagoon as the clarifier waste. After a backwash and before a filter is brought back online, the process called filter to waste is performed. Clarified water flows through the filter for a short period of time and is directed to the lagoons instead of through the remaining treatment steps. This allows the filter media to resettle and ensures optimal filter performance. We are now in the pipe gallery, which is in the lower level of the plant below the filters. Notice that the piping is color-coded based on its function. Blue pipes for filtered water, brown pipes for waste streams, and so on. The piping in this area also provides backwash supply to the filters for cleaning and directs filter backwash waste to the residuals lagoons outside the plant for recycling. At this point in the process, the water is very clean. However, treatment plants processing surface water add a disinfectant to provide additional protection against bacteria, viruses, and other pathogens. In this case, sodium hypochlorite is added after filtration and prior to water entering the chlorine contact tanks. The chlorine contact tanks, below the floor I'm walking on here, are long and narrow and are designed to hold the water for a specific amount of time to ensure adequate disinfection prior to pumping into the distribution system. Here we are in the main pump room. These 2 25 horsepower pumps adjacent to the filters pump water from the backwash supply tanks onto the floor to the filters for cleaning. After sufficient disinfection of the chlorine contact tanks, water flows into a series of clearwells. These tanks store water that is treated and ready for distribution. Over time, chlorine concentration decreases depending on water quality conditions. Operators ensure enough chlorine is added upstream of the chlorine contact tank so that not all of it reacts. The remaining residual disinfectant concentration reduces the growth of microorganisms in the distribution system. These 3 50 horsepower finished water or high lift pumps deliver water from the clearwells to the distribution system. Chemicals can also be added here as a final step for pH adjustment and corrosion control. The SCADA system is used to control the flow from these pumps, which in turn controls the water level in the distribution storage tanks. The goal is to maintain the water level while allowing adequate turnover, or water level fluctuation in the tanks. This minimizes water age and preserves water quality. Here we are in the chemical room. Some chemicals are delivered in dry form, while others are delivered as liquids. Most systems include bulk chemical storage, day tanks to safely store smaller volumes, and chemical metering pumps. The type of pumps and size of the tanks depends on the chemical and the dose required. Each of these systems is in a separate containment area in case of a spill. Throughout the entire treatment process, online analyzers continuously sample the water quality. Parameters such as turbidity, pH, temperature, UV transmittance, chlorine residual, and many others are continuously monitored and reviewed. Stream and current, a measure of the charge that exists on the small suspended particles in the raw water, is also monitored. Operators adjust the chemical processes accordingly to ensure optimum treatment performance and the best possible water quality. This is the lab. Small sample pumps and piping also deliver water from various points in the treatment process to this sample sink. Operations staff routinely collect grab samples for parameters like color and fluoride to confirm the readings provided by the automated equipment. These samples are tested in the plant's laboratory, which is also equipped with state-of-the-art analytical equipment. The control room can be considered the brain of the treatment plant. Here we have the filter control panel, which controls the various filter operations, including backwash and filter to waste. The SCADA system computer and these screens allow the operators to view, analyze, and control every aspect of the treatment process. This computer collects water quality data from the plant's analyzers and receives information from remote sites such as storage tanks and the raw water supplies we saw earlier. The data tracked here also helps operators be proactive in their treatment approach. They can use this system to adjust the treatment process in advance of surface water quality changes such as forecast rain events. This ensures optimized treatment, regulatory compliance, and the best possible water quality. This plant is relatively unique in the region because it's a zero-discharge facility. All the water that enters the plant is treated and distributed. Many similar facilities have a permit to discharge treatment waste to nearby water bodies. This plant does not discharge to the river, which is better for the environment and makes the plant extremely efficient. The waste streams from the various treatment processes flow into one of three residuals handling lagoons. Typically, one lagoon will receive flow while the other two are in various stages of drying. As residuals flow into the active lagoon, a sand layer at the bottom traps solids. An underdrain system collects clean filtrate and recycles it to the head or raw water end of the plant for treatment. This downward opening weir gate allows plant operators to decant clean supernatant from rainfall or from settling, which is also recycled to the treatment process. Actively removing water from lagoons significantly speeds up drying time for the residual solids and improves the water efficiency of the plant. It also greatly reduces trucking costs for the dried material. Once the residual solids have sufficiently dried, the material is hauled off-site for disposal. After a lagoon is cleaned out, it can be placed back into service and the cycle can continue.
So Alex, what do you think of the new facility?
I thought it was a pretty impressive system, and to see firsthand how we get from that to this is a really good way to learn about the treatment processes that go into producing potable water.